welcome to the final video of this topic on differentiation. Here we'll be learning how to model real-life scenarios and solve some constraint problems with differentiation. Okay, so this involves solving optimization problems and such an important topic, and I can't wait to get to it. So, if you like to pause the video, have a go at this question on this slide here. This is also a nice question. It's a reminder of what topics we already done. Pause the video, have a go at it, and I'll show you next. All right. I hope you've had a go at it. And it's asking us just to complete the square in part A and to find the minimum point, and also in part B to differentiate this expression and find the stationary point for that. So let's see what we can do. So once you and part A is actually asking us to confirm the result by differentiation. So if we complete the square, what do we get inside the square bracket? We'll have x minus 3 and we'll have plus 7 minus 9. Plus 7 minus 9 is minus 2. So this is the answer to complete the square. The turning point is at x equals to 3 and y equals minus 2. So I've differentiated this on the left side here, and that setting the derivative to 0 also gives us x equals to 3. So these two values check out. Notice we now have two ways of finding the turning point. Not only by completing the square, we can confirm the result by differentiation and getting the same value. Now, here, for part B, we were asked to differentiate this quadratic function, right? So, notice that I, just ignoring that part for now, once we set the derivative equal to 0 and solve for x turned out to be minus b over 2a. What I was trying to show you there is that minus b over 2a is part of the quadratic formula. Notice that this curve is symmetric, isn't it? So what we're finding with minus b over 2a is that the x value is where the x value is symmetric. This part is where we add that square root, and this distance is symmetric because we are subtracting the same square root. So that's why we get two symmetric answers around the turning point. Okay, so if you didn't do this, there is some fascinating results there, I believe. Okay, so let's get to the meat of this topic. This last topic is about optimization, believe it or not. This is a very simple example. It says, given that the total volume of a expanding sphere, imagine someone is blowing up a balloon that is perfectly spherical. So the volume is given us by this formula here. Find the rate of change of volume with respect to radius at the instance where the radius is 5. So we have the formula v equals to 4 over 3 pi r cubed, and we are looking for rate of change with respect to radius. That's what it means. I did tell you that sometimes you have to differentiate with respect to other variables. This not always in terms of y and x. So this 4/3 and come out with us for a ride, because they're just constants, they remain as constants at the front, and when we differentiate, we'll simply multiply by this 3 and that 3 cancel away, so finally we'll have 4 pi r squared. So the rate of change of with respect to r is this here. Now we also need to evaluate it at the point where r is 5. So what does that mean? That means substitute 5 for radius, and that gives us 100 pi. Now, is there anything to note about volume with respect to radius? Not really. Okay, So let's look at another example where we have some things that are really crucial to find. Sorry. So actually 100 times pi, it is 314. We have centimeter cube here divided by centimeter because we are divide we have the powers come down from r cube to r square. So this is my answer wasn't wrong. It's just 100 pi is this number. 100 times 3.14. So write a little sentence that the sphere is expanding at this rate. Okay, per centimeter cube per centimeter increasing radius. Okay, so now here is a problem where you have optimizations to do. So you have a utility function, a consumer consumes products X and Y, and her utility function is given by x squared plus y squared, and is vis-a-vis of each product that she consumes. If you're not familiar, this is an economics example. So price of product X is £1, price of product Y is £2. The total income of her is basically budget for spending on these two products is £120. Okay, so then we are asked to form a utility optimization equation and solve it to find how many units of each product she can consume to maximize her utility function. Okay, so this is the utility function. Now, here's a perfect example where you have two variables in the function. And what is the point of this example is that we have a budget constraint. Now, I've used the word budget here. We always have some sort of a constraint in these kind of in these questions in this last exercise. It might be a volume constraint, it might be a perimeter constraint, it might be in some parameter or circumference constraint, it might be area constraint. Okay, with this constraint, you have to pick it up from the question here. It's telling us two £2 per unit of y. So we can write 2y plus £1 per unit of x. This is the constraint that we write here. Now this is a linear equation. In some cases it might be more has higher powers, but this is the point where you can write one variable in terms of another. So we can say x is 120 minus 2y. So where you have this a utility function given to us in terms of two variables, the point of us is our objective is to use that constraint so that we can rearrange it and write the utility function in terms of one variable only, because we can at the minute we've learned only to differentiate with one variable functions. Okay, so this is a two variable problem, and it's not going to be I'm not saying it's impossible. If you study further maths at university, you can differentiate with respect to two variables, but that's not our point. We are to differentiate, use the budget constraint here to rewrite x here, as I said, I'll put up there, I'm just putting it down here, and wherever we have that x squared now, we're gonna use this expression 120 minus 2y rather than the x. So that's fine. Now we have expanded this bracket and everything is in terms of one variable. One variable which is y. Doesn't matter what the name of the variable is, you can this function now, notice I've written it like y comma y there to indicate that it's one variable. So now you can differentiate. What are you going to differentiate this with respect to? Because it's got y's in the equation, you're going to differentiate this with respect to y. But before that, let's tidy this up. 4y squared can be added with one y square there at the front, so we have 5y square. Then now is the time to differentiate. By the way, this is a graph of that utility function. Utility function is somewhat a misnomer. If you this it could be any of these curves here. It doesn't tell us what's the constant value. It's like you looking at it, you might think of it as equation of a circle, and you won't be wrong. They look like circular curves there. Okay, so I've drawn a few lines here because we are looking for to maximize it. We want to push it out as far as possible. So we want to differentiate this line with respect to y, we said. So let's do that, and we're going to get this expression here. And now what do? I put it equal to 0. Once you differentiate it, you almost always set it equal to 0 to find the coordinate of the turning point. In this case, we are finding the y coordinate. Now put the x here and y there on the axis there. So turning that equation for y, we get y values 48. And that y value, we substitute back just like solving simultaneous problem. We substitute it back into either of these equations here to find x. Actually, this one would have been better. 120 minus 2 lots of 48 will give you 24. That's how I found these 24 units. Okay, and okay, this is the working out for that what I just wrote, and therefore, so we are saying that's it, we've solved the problem. We found the quantity of y to buy and the quantity of x to y. And notice where the graph is, you can check actually that 24 times 1 plus 48 times 2 gives us the maximum amount that we could have spent, or the person, the consumer could have spent. And if we go ahead and actually check out the graph here, the y value is exactly somewhere between 50, which is 48 there. And if you check out the x value here is some number between, yeah, it is actually 24. Okay, so I hope the point to take away from this question was to rearrange the budget, or find the equation that you can rearrange and substitute into the function that you're maximizing. We are maximizing, read the question, we maximize utility. So that means maximizing this function here, but it has two variables and we need to turn it into one variable function. Is there another way of solving this problem? Yes. You could have rearranged this equation to to isolate y, make y the subject. Here we made x the subject, but we could have done it another way. We could have done it like so. We could have said 120 minus x divided by 2. Now I didn't want to use fractions in my working out because here I would have 60 minus half x, and then I would have to rewrite the utility function as x comma x. That means that where I have x square, I would have, no, sorry, where I have the y square, I would have got rid of the y. I would have left x alone, and I would, instead of y, I would have to written x 60 minus x over 2 and square this. Now I didn't want to use fractions, but you can go ahead and expand that if you wish. You would get x square plus 3600 timesing these two and then timesing it by 2, actually we get 60x because half cancel away, and we will end up with the x square over 4. I didn't like to work with these fractions, but you can add this x square and quarter of x, you get 5 over 4x square plus 60x, 1600. This is the utility function in terms of x, and you can differentiate now with respect to x. You would get 4x to the power of 1 plus 60, and if you set this equal to 0, I guarantee you will get the same x value. You will get 24. Let's see. So 60 would go on the other side and become error somewhere. I think there was a minus sign. Yes, this should have been a minus sign, a minus here. So we would have a minus sign. My bad, apologies. So now I noticed that, at least I noticed, I caught myself. Yeah. So here we are setting this equation here equal because there was a minus sign there. So here, to solve this equation, we would have got 60, and we would have needed to multiply it by 4 over 10 to turn that x on its own. So multiplying that means that 6 times 4, which is 24. This confirms our result. We would have got exactly the same value of x. Okay, so I showed you how to do it with two different ways. You can rewrite the budget either in terms of x, and rewrite the utility function either all in terms of x or all in terms of y. Just do one of them, and that will solve your problem. So let's look at yet another example. Uh, that's all right. So in this question, we've been given a tank which doesn't have a top on it. It says it has no top. So it has 5 sides: front, back, left, right, and bottom. So and it says it can be made up of that sheet 54 meter square. Therefore, if I draw you the net of this, it would just have five sides. So those are the parts of the question that we need to prove. Let's just redraw the net of this share. It has x squares at either end, x square here and x square there, because these dimensions are x and x. Here we have yx, and on this side we get yx and yx as well. So it's this the 4 meter square is actually, I'm not reading the rest of the problem. It's saying to show that volume can be written like so, maximize the volume, blah blah blah. But from this constraint here, I'm reading this area as a constraint. Okay, so this is our constraint, where you can our constraint is in terms of two variables. So we've got 2x squared plus yx equals to 54. We can rearrange this constraint and write it in terms of get only one of those variables. Now, looking at the volume, look, they've eliminated in this equation, they've eliminated y. Therefore, we can make y the subject of this constraint equation, make y the subject, so that we can insert it into the volume of this tank. The volume is not hard to see, is volume of a cuboid is all three dimensions multiplied with each other. So x squared y is the volume. So this is our original definition of volume. We're using the surface area, or the net of the shape here, to y the subject. Alright, so let's get to that. That means that, first of all, I'm going to keep yx on the left and subtract 2x squared from both sides, and I end up with this expression here. So then I need to divide by x. So dividing by x leaves us with 54 over x and minus 2 x squared over x is just 2x. All right, so that's a definition of y. Now we're gonna substitute that here. We're gonna keep x squared where it is. Instead of y, I'm gonna open a bracket and write 54 over x minus 2x. And expanding this bracket, I end up with what? 54 x, because the square on the top cancels the denominator, and I end up with 2x cubed. Is that question me? It should be 18x. So did we go somewhere? What went wrong? Hmm, so yes, I see. I made an error here. I messed up. There should be 3 there. So we said that the is in terms of two variables, and we were told that this area is equals to 54. So algebraically, it's 2x squared plus 3 lots of xy. Now this area must equal to 54. Therefore, we we look at our question, and it's saying that prove that show that the volume can be written in terms of so they've eliminated y from this equation here. Therefore, somehow we will make the y the subject of this formula so that we can insert that the volume function. The volume function is x squared. Think about it. Cuboid has volume of all three dimensions multiplied with each other. So y times depth times height. Okay, so that's what we're doing. So making y the subject of this formula. All right, let's do that. That means that we're going to keep. I purposely left the top. Uh, I there should have been a 4yx, but it does say there is no top, so this is 3x plus y rather than 4. So making y the subject, that means that 3xy equals to 54 minus 2x squared, and divide both sides by 3x. I'm just gonna write 54 over 3x and 2x squared over 3x. So simplifying that, 54 over 3 is 18. So that's 18 to the power of minus 1. No, uh, oh, and then I will have negative 2/3 x. So 3 to the power of x squared. So somehow 2x squared 54 divided by 3. Uh, Why why is this not working out? Yeah, no. It's all good. Sorry, my bad. This is the definition of y. I was worried. I was looking at the wrong formula. I have not finished. That's why. So don't panic. We just rewrite the volume as x squared times y, and instead of y we need to have x to the power of minus 1, or put it in the denominator if you wish, 2/3 of x here, and multiply out the bracket. So we will have simply an x, because the powers will give us power of 1, and then 2/3 of x cubed. Now is the time to check our answer makes sense, and volume is exactly what we needed it to be. Alright, so panic over. Of the tank. So to answer, we've answered part A. We showed that it's like so. The volume can be rewritten. So we eliminated y by using the constraint and substituting the constraint. We really this is still the constraint that we line there. Okay, the top line. So now is time to differentiate this volume with respect to x and set it equal to 0 to find the maximum value for tank. So maximum volume for the tank. So we will get 18 minus 3 times the third is going to cancel out the 3 in the denominator. We're left with minus 2x squared, and we're going to set it equal to 0 and solve it. So 18 will equals to 2x squared, x squared is 9, and I'm going to take x to be a positive 3. I'm discarding the square root of 9 to be minus 3 because the dimensions of the tank cannot be negative. And finally, so we've been asked to justify the value of v we found is maximum. How do we do that? We answer justify by finding the second derivative with respect to x. Okay, we do that. That means that differentiating this function one more time, 18 is a constant, so it hasn't got any derivatives. Minus 2 times 2 is a minus 4x. Remember that? So the second derivative, we evaluate it at x equals to 3. Now this is going to give us minus 4 times 3, which is a negative 12. Remember, all that matters is this magical sign at the front. It is negative, and we know, remember, f double dash of a function is whenever that's negative, this implies that it's a maximum. Okay, so the examiner will know what you're talking about. You say the second derivative is less than 0, therefore it's a maximum. Therefore, this implies that it's a maximum. The value of the turning point is x equals to 3. You say therefore x equals to 3 gives us maximum, gives us the maximum. Okay, so did we answer all parts of the question? Yes, we did. Alright, so let's see if there is yet another question here. So here's a neater version of the same work here, and it's exactly what I've done by hand. Okay, so we went through the working out, we found the x to be 3, and so on and so forth. So uh, and this is telling us the justifying that what value we found for x is giving us a maximum volume. All right, so and you can actually check the graph, and you can actually substitute the value of 3 back into the volume function to find the actual volume, and you will find that the volume will be 36 meters. Okay, but that's not what we were asked to find, so I didn't bother substituting it back. So in this next question, we are looking at displacement formula here. This it comes up a lot in the final chapter or final few chapters of a book, applied book. So here a pebble is thrown vertically upwards, and its height above the no above the top of the cliff at time t is given by this equation. Find the maximum height that it reaches when this occurs. So you need to uh, differentiate this to find at what point it will reach the maximum height. So what what does that mean? I'm familiar with velocity function, but velocity is rate of change of distance with respect to time. Therefore, in our case, S stands for distance or displacement, and it's only talking about the vertical, so it's only in one dimension here. So when you differentiate this with respect to time, this function is given to us in terms of t. So we're going to get 10 minus 10t, and you're going to set that equal to 0. At the highest point, at the in an instance, there is an instant where velocity is zero. It was positive going up, and if velocity does have a direction, it will turn into negative when it's coming down. So at time equals to 1 second, it has reached that maximum. So you substitute that t equal to 1 back into the original function s to find the maximum height. So you find that it's 5 meters. 5 meters, it was measured from the top of the cliff, so you say 5 meters above the cliff. And if there is more to learn about it, so displacement, when you differentiate it, you get the velocity formula. If you differentiate the velocity formula with respect to time, you have found the acceleration of the object. And if you have acceleration formula and you want to find the velocity formula, you will integrate it with respect to time. And if you do have the velocity formula and you want to find the displacement formula, you integrate it with respect to time. By it, I mean integrating the velocity function with respect to time. Now, we will study integration in the next chapter. So there's more to come. There is a appetizer for you there. But before we go, you can read this example, and we've been asked uh, to. It says a square piece of a card has side length 20. We want to cut out and fold it into a box so that we want to maximize the volume of the box. So it's saying that show that the volume of the box is given by this function v, and then find the exact value of x that maximizes uh, that volume. So pause the video, have a go at this problem, and then I'll show you the answer. Okay, so I hope you have had a go at this question, and this x here is we will have to cut out squares from the corners so that the area reduced somewhat, and the volume, we've been told that express the value of y in terms of x. So won't be told this, you have to know this, that volume is going to be uh, written like so. Okay, so I hope you have had a go at this problem. Now this volume is x y square is telling us that really after folding this length here is y. Okay, the y is square, this length of this square here, where you after subtracting x's here. Now if you think about it, you've subtracted how many x's from 20. You have been told 20 is equals to 2x plus y, therefore y is 20 minus 2x. So you substitute this into the volume formula. So we know that the volume is x times y square. So volume is x square, x times y square. So then volume becomes x times 20 minus 2x squared. So expand the bracket there, and then differentiate this expression with respect to x. Alright, so once you've done that, you're going to set it equal to 0 and solve for x. So the general pattern is always the same. Solve for the, the remaining variable that's left in the function. Uh, okay, solve for x, and then uh, you substitute it back to find the volume and also find the value of each dimension. So when I rub this off, the answer looks something like so. So we said that volume is xy square. So we're replacing 20 minus 2x for y, and we're gonna expand this bracket. So that at this point, after expanding this, we have answered part A. Okay, so here is where you get your marks for part A, and then that should give you some confidence that you have solved the problem so far correctly. And to find the max value of x that maximizes the volume, that means to differentiate it, set it equal to 0, and you get two values. Which of these x values makes sense? It wouldn't make sense to be 10, because if x was 10, we would have cut out halfway of 20 from there and halfway of 20 there, and we would have zero volume. Cutting out x to be 10 is going to be not helpful, so that gives us volume of 0. So we take x to be 10 over 3. So, and you can substitute that back into the volume formula to find the actual volume that's maximized. So with that, I hope you enjoyed this chapter. Here are some more challenge questions. Actually, these are not challenge questions, they are rather simple questions. These I'm thinking, and I wish you the best, and I'll see you in the next chapter where we'll be talking about integration.